So I'm going to try and explain what I understood from the lectures of advanced kinetics for the derivation of the Eyring equation. So the Eyring equation is the final outcome from the activated complex theory, right? So what happens is you have the reaction A to B, and we model this as being a intermediate complex which then breaks down to products, right? So we know from our general understanding of kinetics, uh, rate d product over d time, right? Rate of change of products over time is equal to, let's just say, put a simple k here, right? Rate constant. It's going to be this simple k multiplied by this, right? So we need to get an expression for this one. How are we going to get that one? We consider this equilibrium, right? So there, when we talk about the equilibriums, I introduced rate instead of a normal Kc or a Kp, right? He introduced a proportionality constant, right? Uh, Goes like this, right? And the final equation, we can write the proportionality constant like so, right? K C over concentration of A into concentration of B, right? So now we can substitute, we can subject this equation, we can subject C double dragon. Okay, that's a little, I keep making that mistake. Concentration of C double dragon, right? So concentration of C double dragon is equal to this proportionality constant into CA into CD, right? Alright, okay. So now where did we get this proportionality constant from? Normally we would write Kc equals concentration over Ca divided by Cb, right? This would be the typical equation, but we replace Kc with Kp, and this we get a proportionality constant when you replace Kc with Kp. Right, to do that you have to use P equals NRT, do a whole substitution, and ultimately you arrive at this expression for K double prime, right? So I'm gonna write that in the side over here as well, right? Another expression, let's say for K double dragon, is RT over P naught, right? Kp. We're gonna keep this in a side, right? This is kind of, we'll come back to this expression, right? Now we take this one and put it here, right? We take this equation, right, and substitute it there. So you have dp over dt, which is the rate, right, equal to k into capital K double dragon Ca dot Cb, right? Now remember we're talking about an elementary reaction, right? So normally based on our general knowledge in kinetics, we usually say rate is equal to K2 concentration of A concentration of B, because it's an elementary reaction, right? So you can compare these two and then see that K2 is equal to this simple K, which is the rate of this breakdown from activated complex to product, and then the proportionality constant, right? So for us to get an expression of K2, we have to find out two equations for this. So everything else that we do in the rest of the discussion is to get there, right? Now, let's. So we need to get an expression for K2. To get an expression for K2, we need to get an expression for K double dragon and this simple K. So we start working out double dragon from We have an expression for K double dragon, right? We have this expression, but we have a Kp here, right? Kp is a bulk property, it's a thermodynamic term. Um, and when we're developing these kinetic models, we think about the individual collision event, not about uh, the bulk reaction, right? That we are developing this model by looking at the individual single reaction, not the bulk. But Kp is a thermodynamic term, and thermodynamic terms are generally, not generally, they are by concept bulk properties. So that leaves us with a problem. I mean, to describe K double dragon with this Kp over here, uh, it's there's a conceptual mismatch, right? So we are looking at the micro event, and we have a thermodynamic term, which is a bulk term, which describes bulk phenomena, and you can't come up with a Kp value by looking at an individual event. You can't make that connection generally. Uh, but we have an entire section of thought that connects micro events, right? Uh, Connects micro events or micro phenomena to bulk phenomena, right? So this bridge between micro and bulk, that's statistical thermodynamics, right? That's statistical thermodynamics. I hope you guys can read that. I'm sure you can read that, right? So this connection between micro events and bulk phenomena is in statistical thermodynamics. Under statistical thermodynamics, you have a definition for Kp, right? So Kp definition for stat under statistical dynamics. Let me take another colored pen. Okay, there you go. So Kp definition under statistical thermodynamics is this one: pi I into q partition coefficient of particular species, total partition coefficient, divided by Na to the power of nu I, which is the stoichiometric coefficient, multiplied by E exponent of change in energy over RT. This is the definition, right? I don't know where this came from. Uh, I'm sure there's a very nice development about but that's beyond the scope of this discussion. Point is, when you apply this description, this equation for the equilibrium that we are looking at, right? So let me revisit the equilibrium we are looking at, which is this one, right? This is the equilibrium that we are trying to define, we are trying to study and quantify or rather analyze with an equation, right? So then you get a value for Kp according to that. Again, I am not going to spend the time expanding on that equation. If you substitute the values for that one, we arrive at a expression NaQC divided by QA. I don't know how to read this circle and cut thing. So yeah, there you go. This is the expression that you get, right, for Kp. All right. So now, um, in the when modeling this reaction, right, we are modeling a elementary reaction, and we are modeling it as right, this is the elementary reaction, right, this is products, so reactants and then products. So there's a hill and then it falls back like this. You have A and B here, and you have C double dragon here, right? So here, uh, this part we say it's an equilibrium, right? uh, and here this activated complex, we I find it easier when we think about it as uh, let's say kind of a molecule, which has a particular set of bonds, right? and one of the bonds in this activated complex has to break down one or a certain set of bonds has to break down to produce the products, right? So uh, when we talk about bonds breaking down, how we think about it is, right? Let's come back over here, right? Let's just say you have A, B, and then some kind of, what I'll draw an arbitrary diagram, right? So you have sort of, let's say this is your A, this is your B, right? They two, what will look too same? That's not good. Uh, let me draw. Like this. This is your B with a bit like that, right? Okay. So okay, let us use different colors just because we can. This is your B, right? And there are these bonds, right? Let's say this is your activated complex, right? This is A, this is B, and let's say the whole thing is your activated complex, right? So for you to get your product, you want to draw the product, let's consider that this bond and this bond servers, right? So your product is going to be something like this with this one, right? So what happens with from at the final stage, right? Is at least the way this concept is modeled and the way I understand it is, when going from here to here, right, from the activated complex to the product, we think about it as a vibration going overboard, right? So you have this there's this bond vibration and there's this bond vibration, right? So if you just think about a bond and it's kind of vibrating like this, if it vibrates beyond a certain point, it would break, right? And the two parts would go away from each other, right? The world is really changing um, from here to here, right? From here to from the uh, again. What I'll do is I'll only consider that one bond breaks. Otherwise, it becomes a little hard to explain. Right? Only one bond breaks. So from here to here, we assume that the only thing that changes is the uh, vibration. Right? Everything else is same. That's the way this model is designed. And so when the vibration occurs beyond a certain energy level, it, the one breaks, right? That is what is denoted by this Morse curve as well, right? You have, this is the ground level, and the you increase the energy, the vibration increases, and at one point, this vibration just goes, it goes to infinity, right? The bond breaks. The usual potential energy versus bond length diagram, the Morse curve, right? So in this expression, right, each Q term includes all of the partition coefficients, right? And each Q term tells us how the energies of all different four forms, right? Let's take Q, this one, right? So it actually talks about Q translation of C, and then Q vibration of C, Q rotation of C, and then Q electronic of C, right? All of this is modeled inside this term. It's included inside that term, right? And what we are saying is that this is the only one that changes. The vibration is the only one that changes, right? So we take that out and consider all of the others to be constant, and we all of the others to be constant, right? And we put this term, we we use a single letter, right? This Q shy, or what, I don't know, man, what this is, right? What Q bar, right? is equal to q translational into q rotational into q electronic, right? This product of these three is q bar. We consider it that way. And then for this one, from statistical thermodynamics, under certain conditions, right? There are some conditions, right? Temperature has to be above a certain point. I believe above the vibrational temperature, you have the equation that QV is equal to, I'm not sure about that, but my memory is that it should be above vibrational temperature. QB is equal to KB of HT over nu, right? So you come up with this expression is equal to this. So you have a single expression for C, right? Now we substitute this one in this, right? And we get a new equation for Kp, right? Where are we? For Kp, we come up with a new equation, which is Na. We substitute the Qc over here like this, the bar, right? And then you have, what I'll write the part that we substitute in a different color, right? Uh, Continue. Here you have Qa, Qb, right? The part that we substituted is this, right? We are substituting this, and this term includes the vibrational, sorry, not the except vibrational, the others, which is translational, rotational, and electronic included in this Q bar. Vibration 1, we have written it outside like this, kbt over h nu, right? So what is this nu? Nu is the vibration of that bond, right? The bond it changes. Nu is the vibration, right? So this is the expression for Kp based on statistical thermodynamics. Statistical thermodynamics is based on it connects the uh, micro events, right, to the bulk events. As you see from micro events, now we have a equation for the bulk phenomena or thermodynamic phenomena. All right, so you have an expression for Kp now. We have an expression for Kp, right? Now we can go and put it in there, right? Uh, I'm gonna give this like a name. I don't know. Let's call it equation 1, right? So in equation 1, we substitute it for K double dragon, right? From 1, K double dragon. We had RT over P naught, right? RT over P naught into Kp, right? So Kp, we substitute this whole lot over here instead of Kp. So we write this part here, right? Multiplied by Kp. So here you write NaQ over C Kb T over H nu Qa Qb. Alright, so you have this expression. Now we have an expression for K double dragon. Because there's so many things going on in this one, what we do is we modify this expression like this. K double dragon equals, we keep this one out, right? This is the vibrational partition function. That's what's going to be changing during the course of the reaction. So we write it outside like this. Kb over T H nu can move because all of these are constant, right? Standard pressure Qa is a constant because nothing is changing in the A molecule. Qb is a constant, and this represents all of the partition coefficients which don't change. Na is the Avogadro number constant. All of them are constants. So we say K bar, right? That's a constant, right? So what is K bar again? We will write that over here on the side. Okay. K bar is equal to, we are going to say RT over T naught. Okay. Here we are going to write K2 bar. Why are we saying K2 bar? All of these terms we represent it using this K2 bar. So again, for clarity's sake, we'll also write the definition of K2 bar as we have defined it to write it here. NAQ bar, right? It's really important that we don't forget that bar. Uh, right, QA dot QB, right? So you have a, so you can see that this K2 bar is basically K2 except without including the vibrational partition coefficient of the activated complex, right? It's exactly the same expression as K2. Sorry, I'm sorry, KP bar. It's exactly the same expression as KP uh, without the vibrational partition coefficient, right? So there you go. You have an expression for K double dragon, um, which computes, right? Which is entirely based on the micro event that we are modeling. Now let's go back again, right? So what we are trying to get is an equation for K2, right? So this equation, right, is what we are trying to work out. So here you go, K2. So I am going to define this one as equation number 2, right? So equation number 2, right? So in equation number 2, right, you have in equation number 2, which is K2 is equal to a simple K multiplied by K double dragon, right? So we have a definition based on the micro events for K double dragon. So how do we define this simple K, right? So what does this simple K represent? It represents this slope in our reaction coordinates, or rather the energy potential energy diagram, right? The reaction coordinates diagram, I suppose, right? So this one, A, B, you have your C double dragon and then your products, right? So this simple K, it represents this drop, right? And earlier here we talked about the idea that uh, the, the bond is vibrating, right? So it's kind of trying to break. It stretches, and when it stretches, it should break, and sometimes it collapses back. So that's a compression and then stretch, right? So you have like the bond, it stretches outwards. It may break when that happens, but sometimes it comes back, right? So each time it stretches, there's a chance that it breaks, right? So we can say, I mean, we can think that, let's say there's a 10% chance that if it stretches beyond a point that it will break, right? So we can say the rate of this breakdown is the frequency. How many times does it stretch out? Multiply this by 10%, right? I hope I made sense there, right? Let me try to explain that again. Let's say that this is the bond that's going to break, right? So it's going to stretch and become like this, right? Kind of like a rubber band you're pulling too far. It stretches, right? It is about to break. So that let's imagine there is in this example, let's say 90% chance of it. I think that's a bad number that I chose. And let's just say there's like a 70% chance, right, of it breaking at this point, right? So if it stretches 100 times per second, that is frequency equals 100 times per second. That's a 70% chance of it breaking. In a second, 70 of these bonds should break, right? So in other words, in a second, 70 of these activated complexes should form products, right? So this F equals, okay, right? F is 100, right? Let's say the rate uh, of this step, let's say step 2, right? Rate of step 2 is going to be 100 times. It stretches to the breaking point, but out of that, only 70 of them break. right? So this is the frequency. This is the rate, right? So it's going to be 70. Now, if f turns out to be 500, right, R2 would become 70 into 5, 350, right? That's the idea that it is based off of, right? So we can write this concept as an equation, right? K equals frequency, right, multiplied by the success rate. How often does a breaking stretch result in product formation? That is kappa, right? So you have an equation for K, simple K, which is the final rate equation, and where did my cursor go to? Okay. So and you have an equation for K double dragon, so you can put both of them together and finally get the Eyring equation. So K2 is equal to in the Eyring you have KBT over H nu multiplied by nu into kappa, right? So the two nu's will cancel off. So you have so you have KBT kappa h to the power minus 1 Eyring equation. Alright, so how much? 26 minutes. Okay, I hope that was helpful.